Hello, in this video we'll be working through Unit 5 homework problems 13 through 20. For number 13, we want to determine if the mean value theorem is true for f of x equals negative 2 plus 1/2 times the absolute value of x minus 3 on the interval from 0 to 5. If it is, we're going to find the value of c guaranteed to exist by that theorem. For the mean value theorem, there are two conditions that we need to check. We need to make sure that our function is continuous on the closed interval from 0 to 5 and differentiable on the open interval from 0 to 5. So since this is not a polynomial function, we want to think about what the graph of this function looks like. That's the easiest way to sort of figure out if it's continuous and differentiable on our interval. So you should be able to picture this graph if you know your parent function, your parent absolute value function has a V shape. There's a corner point at the origin. So at the corner point, our function is not differentiable, but is the corner point for our function f of x going to be in the interval between 0 and 5? So we can think in terms of transformations. Our function f of x has been shifted from the parent function right 3 and down 2. So you might be able to just think about that and figure out the answer here. If not, let's go ahead and graph it using the calculator. So we want negative 2 plus 0.5 times the absolute value of x minus 3. So f of x has a corner point at x equals 3. It's continuous everywhere, but it is not differentiable at x equals 3, and x equals 3 is in our interval. So since f is not differentiable, on the interval from 0 to 5, the mean value theorem does not apply. Number 14, determine if the mean value theorem is true for g of x equals 2x plus sine squared x on the interval from 0 to 5. Give a reason for your answer. If it does hold true, find the guaranteed value of c. Is our function continuous? Well, just looking at the equation, we can see that there are no discontinuities. There is no value of x that is going to produce a non-real number. So the function is continuous everywhere, but is it differentiable everywhere? For that, we can either look at the graph and make sure that it doesn't have any points that would be not differentiable, or we could find the derivative and see if there's anywhere the derivative equation would not exist. So those are two different ways we can figure out if our function is differentiable on our interval. Let's go ahead and look at the graph. So g of x equals 2x plus sine squared x. So sine squared x means the sine of x squared. And when we look at the graph, we only have to look on the interval from 0 to 5. So I cut off the right side of the graph a little bit there. Let's adjust our window. So looking at the graph, I can see that it's smooth all the way from 0 to 5. There are no places where this function is not differentiable. So it is differentiable on our interval from 0 to 5. So the first condition we check, g is continuous on the closed interval 0 to 5. And then we have g is differentiable on the open interval from 0 to 5. So the mean value theorem does apply. And now we're asked to find the values of C guaranteed to exist by this theorem. Well, this theorem guarantees that somewhere G prime of C is equal to the average rate of change of G on our interval. So G of 5 minus G of 0 over 5 minus 0. So we're going to find G prime of X, we're going to find the average rate of change, and then we're going to set those equal to each other. G prime of X equals 2 plus 2 times the sine of X times the derivative of sine X. We're using chain rule to take the derivative of sine squared X. So G prime is 2 plus 2 sine X cosine X. And I want to set that equal to my average rate of change. So the average rate of change, I need to know G of 5. I can see I've got already the table displayed here that G of 5 is 10.92. And I'd rather have 3 decimal places, but I'm assuming that the last digit there rounded that up to 0.92. So we'll say 10.92 minus G of 0, I can also see in the table there is 0, over 5. So I need 10.92 divided by 5. And I want to make sure I'm working with as exact values as possible. So I'm just going to go ahead here on my home screen and find G of 5 again. And then we needed to subtract 0, which isn't going to change the number, and then divide by 5. So I get 2.1839. So now we want to let our derivative equal that average rate of change, 2.1839. So we're going to enter our derivative equation, 2 plus 2 sine x cosine x. And we want to know where does that equal 2.1839. And let me fix my window here. So 0 to 5 for our x values, but my y values, it's looking like maybe 0 would be a good y min, and 5 would be a good y max. Okay. And now we have 1, 2, 3, 4 points of intersection on our interval between 0 and 5. So there are 4 values of C that satisfy the theorem. So let's find each of these points of intersection. So we have C is approximately 0.092. Okay, the next one. $1.478. $3.234. And finally 4.619, so we'll say 4.62. Number 15. For t greater than or equal to 0, the temperature of a cup of coffee in degrees Fahrenheit t minutes after it's poured is modeled by the function f of t equals 68 plus 93 times 0.91 to the power t. Use your calculator to find the value of f prime of 4. Using correct units of measure, explain what this value means in the context of the problem. We're going to find the numerical derivative using the calculator. So first we want to enter our equation. F of t equals 68 plus 93 times 0.91 raised to the power t. So we have our function f of t in y1. I'm going to go to my home screen, and I'm going to use math 8 to find the derivative at t equals 4. So math 8, and then d over dx, we're taking the derivative with respect to x. What are we taking the derivative of? Here you can type out the function, or since I already have it typed into y1, I can just call up y1. So to get to y1, I'm using alpha f4, and then 1 for y1. And then we want the derivative specifically when x is 4. And we get negative 6.0146. So that is the value of f prime of 4. Negative 6.015 if we round to 3 decimal places. Now if we come out of function notation here and we go with Leibniz notation, our derivative is the derivative of f, the temperature in degrees Fahrenheit, with respect to t. So df dt equals negative 6.015. And this helps me figure out my units. The derivative of my overall temperature function, so that was degrees Fahrenheit, over the change in time, and the time here was measured in minutes. So the units would be degrees Fahrenheit per minute. Those are the units of measure, and now we have to explain what this value means in the context of the problem. So first of all, notice that it's negative. And when your derivative is negative, it means the function that you were taking the derivative of is decreasing. So at this particular moment in time, which is 4 minutes after it's poured, so 4 minutes after the coffee is poured, the temperature is decreasing at this rate. So we could say something kind of generic like at time t equals 4, or we can try and put it more in the context of the problem and say 4 minutes after the coffee is poured, its temperature is decreasing at a rate of approximately 6.015 degrees Fahrenheit per minute. Number 16, administrators at a hospital believe that the number of beds in use is given by the function b of t equals 20 times the sine of t over 10 plus 50, where t is measured in days. So our function b represents the number of beds, and then t is measured in days. So b of t, number of beds after t days. Part A, use your calculator to find the value of b prime of 7, so the derivative of b at 7. Using correct units of measure, explain what this value means in the context of the problem. And then for time t between 12 and 20, what is the maximum number of beds in use? So we want to find an absolute maximum for part B. Part A, let's find b prime of 7. We're going to do this numerically on the calculator. So I will enter my equation, make sure that you are working in radians. So our function is 20 times the sine of t over 10 plus 50. And we want to find b prime of 7. So math 8, derivative with respect to x. I can type out the equation for b, or I can call it from y1. So to do that, alpha f4, 1 for y1, and then I want the derivative at x equals 7. Right, so we get 1.5296. If we round to 3 decimal places, 1.530. b prime of 7, 1.530. And the units there, this is the derivative of b with respect to t, so number of beds with respect to the time in days, beds per day. Explain what this means in the context of the problem. Our derivative is positive, which tells us our function b is increasing at that time, at that moment in time, which is 7 days later. We don't really have a specified starting point, so we'll just say on day 7. Okay, on day 7, or if it's really unclear, we could just say at t equals 7. But on day 7, the number of beds in use is increasing at a rate of about 1.53 beds per day. Part B, we want to find the absolute maximum on the interval from 12 to 20. Let's look at our graph and see if we have a relative maximum. So again, we're on the interval from 12 to 20. So I'm going to adjust my window. We still have our equation for b in y1, and I want to work on the interval from 12 to 20. And we'll just see what kind of values we're getting in our table. So from 12 to 20, we're probably need a max of 70, should do it. Okay. And then our min, I'm going to set that min a lot higher as well. We'll just try and look from between 60 and 70. So we do, I can do a little bit better with that window. Let's go, that's currently from 60 to 70. So let's do 66 to 74. Okay, it looks a little bit better. And we can see that we do in fact have a relative maximum. When you're looking for an absolute maximum, you want to consider your end points and any relative maximums and see which is the highest. So clearly on my graph, I can see that the relative maximum is higher than either of the endpoints. So I'm not going to bother to find the numerical value of the endpoints because I know in this particular case, the relative maximum is my absolute maximum. And to find this absolute maximum, I'm going to go second, calc, number 4, maximum. And then we want to move our cursor a little bit to the left, hit enter, and then a little bit to the right, hit enter one more time, and we have our maximum occurs at time t equals 15.708, and the maximum value is 70. So look back at the question to see if they were really asking you to find the x value or the y value. It says, what is the maximum number of beds? That's the y value. So in this case, that would be 70. the maximum number of beds in use on the interval from 12 to 20 is 70 beds. And for our last set of problems, we're going to use the table given here, which represents values of a differentiable function g on the interval from 0 to 6. Number 17 asks us to estimate the value of g prime of 2.5. So 2.5 falls in between 2 and 3. To estimate the derivative, we're going to use the closest two surrounding points and find the average rate of change. Using the closest two surrounding points and finding the average rate of change is going to be our best estimate of the instantaneous rate of change. We don't want to go too far out. We want to stay as close as possible to the actual point we're interested in. But in this case, that would be 2 on the left and 3 on the right. So we're going to find the average rate of change. We want to find g of 3 minus g of 2 over 3 minus 2. This is the average rate of change on the interval from 2 to 3. So that's going to be 5 minus 1 over 3 minus 2, or 3 minus 2, or 4 over 1, which is just 4. Number 18, if one exists, on what interval is there guaranteed to be a value of c such that g of c equals negative 1? We can use the intermediate value theorem for this problem. I'm guaranteed that somewhere g will equal negative 1 if I can find two endpoints where negative 1 is in between the y-coordinates of those endpoints, because I know that I have a continuous function. And I know that g is a continuous function because I was told that it's a differentiable function. And if it's differentiable, it's automatically continuous. So can we find 2 points, one where the y-coordinate is less than negative 1 and one where the y-coordinate is greater than negative 1? Well, right here, negative 3 is less than negative 1, so when x is 0. And when x is 2, the y-coordinate is greater than negative 1. And I don't have to choose 0 and 2. I could choose 0 and 3, or 0 and 4, or 0 and 6. It's still true. But I'm just going to use these closest two right here. So there is a condition for using intermediate value theorem. The condition for intermediate value theorem is that our function is continuous on our interval, and it is. G is continuous on, now we were already told it's differentiable from 0 to 6, so I could say it's continuous on 0 to 6, but what I really need is the interval that I'm using, 0 to 2. If it's continuous on 0 to 6, then it's continuous on 0 to 2. Okay, and so the second part of our intermediate value theorem, our y-coordinate, the solution that we're interested in, has to be in between the y-coordinates of our endpoints. So we have g of 0 is less than negative 1, which is less than g of 2. Therefore, the intermediate value theorem guarantees that g of c will equal negative 1 for some value c on the open interval from 0 to 2. If one exists, on what interval is there guaranteed to be a value of c such that the derivative is equal to 0? The derivative is equal to 0. When you see that right away, you should think Rolle's theorem. That's the conclusion of Rolle's theorem, that somewhere the derivative will equal 0. Now there are three conditions to check for Rolle's theorem. One, is our function continuous on the open interval? Two, is it differentiable on the closed interval? And three, are the y-coordinates at the endpoints equal to one another? So let's look in our table. Let's start with, we already know that it's differentiable, that was given, which means that it's continuous. So condition 3, are there two values where the y-coordinates are the same? And I do see that in my table. When x is 2 and when x is 6, the y-coordinate is the same, it's 1. Okay, so we have all conditions met. Therefore, the conclusion of Rolle's theorem is true. Somewhere on this interval from 2 to 6 in this case, the derivative will equal 0. So let's write down that we checked our conditions. So 1, g is continuous on this interval, on the closed interval from 2 to 6. Again, because we were given that it's differentiable, so that automatically makes it continuous. G is differentiable on the open interval from 2 to 6. It's actually differentiable on the closed interval, but we don't need it to be. We don't need to be that strict. We only need it to be differentiable on the open interval. So it wouldn't be wrong if you used closed interval in this particular case for number 2. But in general, we just need open interval. And then number 3, we have g of 2 is equal to g of 6. Therefore, Rolle's theorem guarantees g prime of c will equal 0 for some c on the open interval from 2 to 6. And our final question, number 20, if one exists, on what interval is there guaranteed to be a value of c such that g prime of c equals 4? Now, it's a little easier when g prime of c equals 0. We just really need to find where two places where the y-coordinate is the same and make sure it's continuous and differentiable. For g prime to equal 4, we have to do a little more work. So this sounds like mean value theorem, which is the more general case of Rolle's theorem. The mean value theorem. Mean value theorem has two conditions. The function has to be continuous on a closed interval, differentiable on the open interval. And if that's true, then somewhere the derivative will equal the average rate of change. So if we can find an interval that has an average rate of change of 4, then this must be true that somewhere on that interval g prime is equal to 4. So we have to figure out, okay, which two endpoints are going to give me an average rate of change of 4. So we might have to do some guess and check here. If I use these first two values, the average rate of change would be 1 minus negative 3 over 2 minus 0. So that would be 1 plus 3 is 4 over 2 is 2. So that's not the one I'm looking for. There's lots of possible intervals we can go here. I can expand like this and now say, well, let me check from 0 to 3. And let's just do this in our head if we can. So 5 minus negative 3 is 8. 3 minus 0 is 3. 8 divided by 3 is not 4. So it's not that one. I can check 0 to 4. 2 minus negative 3 is 5. 4 minus 0 is 4. 5 over 4 does not equal 4. So it's not that one. I can look from 0 to 6. 1 minus negative 3 is 4. 6 minus 0 is 6. 4 over 6 is not 4. So it's not that one. Okay, now we can check, well, what about from 2 to 3? So the difference there would be 5 minus 1 is 4, 3 minus 2 is 1, 4 over 1 is 4. So that's the one I'm looking for, the interval from 2 to 3. All right, so conditions. 1, g is continuous on this closed interval from 2 to 3. 2, g is differentiable on the open interval from 2 to 3. So now I'm guaranteed that somewhere on the interval from 2 to 3, the derivative will equal the average rate of change. So now we have to find the average rate of change. The average rate of change on the interval from 2 to 3 is g of 3 minus g of 2 over 3 minus 2, which is 5 minus 1, 2. I did that before. 5 minus 1 over 3 minus 2, which is 1. So that's 4. The average rate of change is 4. So I know, okay, so we can say, therefore, the mean value theorem guarantees that for some c on the open interval from 2 to 3, g prime of c will equal 4. So that's all there is to it. Make sure you check your conditions, and then make sure you name the theorem that you're referring to. You can abbreviate, and then what does the theorem guarantee for us?